So today's video is about multiplication vector quantities. All know multiplication of vectors is not as straightforward, simple as scalar multiplication. There are basically two kind of vector multiplication. One is known as the dot product, and the second is known as the cross product. Today we will only discuss about dot product. So before discussing dot product, let's discuss some basics. Vector is represented by a line segment, with a direction A towards B, from A towards B, and this is how we represent vectors geometrically. And algebraically, we represent vectors. We represent any vector by its components. Say it's A1 I cap plus A2 j cap and plus A3 k cap. These I cap, j cap and k cap are unit vectors along x-axis, y-axis and z-axis respectively. And how do we find the magnitude of this vector? We find this magnitude as square root of a1 square plus a2 square plus a3 square, and we find the direction with an unit vector by scaling the vector with its own magnitude. And in case of geometric representation, we draw the vector as a directed line segment and we mention the magnitude like this with a mod sign, and of course the direction is the AB cap. So now let's come to dot product. So first I would like to define dot product. Say I have two vectors A1, let's not name this A1, let's say I have two vectors A vector and B vector, and first I will go into algebraic definition of dot product. Say this A is represented as A1i, A2j and A3k, and B is represented as B1i, B3, B2j and B3k. Then the dot product between these two vectors, A vector and B vector, is written as this A dot B, and it is defined as the AI BI with running index I. This is nothing but A1 B1 plus A2 B2 plus A3 B3. So this is my definition of dot product. Now why would we define such operation? This is the question. Why are we defining dot product like this? Let us take the geometric way of definition. So geometric way of defining a dot product is like this. Say we have two vectors, A vector and B vector. Let's say this is A vector and this is B vector, and the angle between them is theta. Then A dot B is nothing but mod of A mod of B, that is magnitude of A multiplied by magnitude of B multiplied by cosine of the angle between them. This is also an absurd operation. And why would we like to define something like a magnitude of A magnitude of B and then multiplying it by cos theta from wherever we don't know? See, the idea is from the definition of A dot B and from the geometric definition. So this is geometric definition. This is geometric definition. What we get is we get the magnitude of this vector we get the magnitude of this vector, and we relate the angle to the definition of dot product. And if we know the components of the vector, we can compute it very easily. So the geometric definition of dot product relates between angles and lengths, and how it relates, that will be clear in this video. Now first question arises, how to go from this definition to this definition. We have defined a dot b like this. This is our primary definition, but we are also saying that a dot b is mod a mod b cos theta. So we have to show that this is indeed the definition of a dot b. Let's do a fact check first. Let's take two same vectors. First take two same vectors, say a dot a. So this is nothing but mod a times mod a, and the angle between a and a is cos 0. So this is nothing but cos 0 is 1, and this is nothing but mod a square. Okay, now let's take the previous definition. A dot a is nothing but multiplying a with itself, and from this the structure of the structure of a vector, and from this definition of the dot product, from this definition, what we will get is this. We will get a1 square plus a2 square plus a3 square, which is nothing but the magnitude of a square. So this check is done. So a dot a geometrically and a dot a algebraically, so they are the same. Now what about two different vectors? So let's take two different vectors. Say this is my a vector and this is my b vector, and this is the angle between a and b. Well, we can also construct a line between a and b, and let's name this c vector. From this diagram, we can write down c is b minus a, b vector minus a vector. And from the previous video, if you have not seen it, you will find a link in the description. From the law of addition of vector, we derived an expression for the subtraction of vectors, and from that we can write that mod of c square equal to mod b square plus mod of a square minus 2 magnitude of a magnitude of b cos theta. Well, this is also called the law of cosines, and you can Google it and you'll find it, the law of cosines. And the law of cosine relates the magnitude of, not actually magnitude, the length of three sides of a triangle. So we have found this quantity. Now we want to find c dot c. From our previous example, we have shown that c dot c is nothing but c squared. So we will find c squared. Now let's compute c dot c. Now let's say this is b dot a, sorry, this is b minus a vector dot b minus a vector. If we expand this, we will find b dot b minus a dot b minus b dot a plus a dot a. Now b dot a and a dot b are same. Why? We can find it from this definition. From this definition. See, whatever I write a2 b2 A3 B3, and if we write B1 A1, B2 A2, B3 A3, they are, that's why A dot B and B dot A are same. So let's write this as, I will take A vector in the front. So magnitude of A square, B dot B is nothing but magnitude of B square, and this is minus 2 A vector dot B vector. Now let's now this is C vector square. Now let's compare these two. Let's compare this line and this line. See, they are the same except from this thing. Here mod A mod B cos theta, and here we have got to A dot B. So we have shown that A dot B is actually mod A mod B cos theta. So this is what we have shown, and we have shown that if we take the algebraic definition of dot products, summation ai bi, then that also implies this definition, mod of A mod of B into theta. Now the question is, what are two definitions good? I have some artificial operations, but what are they good for? Now in we will see what they're good for. So let's take an example, and the example is going to be computing angles. Let's say I have a three-dimensional space. This is my x-axis, this is my y-axis, and this is my z-axis. And let's take 3 points. This is my A, B, and this is my C. Let's say A has a coordinate of what am I going to do? Okay, let's say it's 2, 0, 0. B has a coordinate of 0, 1, 0, and C has a coordinate of 0, 0, 3. What we want to find is, we want to find this angle. We want to find this angle theta. Let's name this thing origin O. So we want to find this angle between AB and AC. Well, for that, what we will do is, we will make this AB vector, and this one is AC vector. If we do AB vector dot AC vector, what we will find is magnitude of AB, magnitude of AC times cos theta, and this is the theta that I have to find. And for doing this, we will use the two definitions that we have learned. So I am writing cos theta as AB dot AC divided by magnitude of AB, magnitude of AC. Now how are we going to find the AB vector? You can find AB vector by defining the position vector of A, position vector of B, and then subtracting the position vector of B minus the position vector. We will not, at least in this video, I will not do that. I will do it intuitively, and I will also suggest you to do that, because it will give you an intuition of vectors, and you will understand vectors more deeply. So we want to find AB vector. So let's first mark the unit vectors. This is I cap, this is K cap, and this is J cap. See, to find this unit vector, to find this vector AB, I have to go from A to O and then from O to B, isn't it? So if I go from A to O, how much distance I'm covering? I'm covering a distance of 2 units. and from O to B I am covering a distance of 1 unit. But while I am going from A to O, I am covering a distance in the opposite direction of I cap. So I will write AB vector as minus 2 I cap plus 1 j cap and 0 k cap. Okay. Similarly, AC vector is minus 2 I cap, 0 j cap and 3 k cap. Now first let's compute the magnitude of AB. If you compute the magnitude of AB, it is going to be square root of minus 2 whole square plus 1 square plus 0 square. It is square root of 5, and magnitude of AC vector is square root of minus 2 square plus 0 square plus 3 square, which is 13. Now I have to find AB dot AC. Now I can find AB vector dot AC vector, component wise, and this is where my algebraic definition will be useful. So AB dot AC is okay, let's say this. AB dot AC is, see, minus 2 times 2, 1 times 0 and 0 times 3. So this is minus 2 multiplied by 2 plus 1 times 0 plus 0 times 3, and this is, oh sorry, minus 2 times minus 2, so this is 4. Now we can easily compute cos theta. Let's now compute cos theta. So cos theta is nothing but 4, which is AB dot AC, divided by square root of 5 multiplied by square root of 13, which is 4 divided by square root of 65. Now theta is cos inverse this. To find this, well, you can put it in a calculator and find the value of this inverse. I will try to find it. 4 divided by square root of 65. This is very near to 64, which is the square of 8. So this is almost going to be 4 by 8. So this is almost going to be half. So theta is going to be almost equal to 60 degree. Now one thing to note is that the cos theta here came to be positive, but this mod of AB can be positive. This mod of AB is positive. This mod of AC is positive, but AB dot AC might be negative. So cos theta can also be negative, and that would imply that the angle that we are talking about is not an acute angle, it's an obtuse angle. So let's write this down. So cos theta, if it's greater than 0, if theta is less than 90. So dot product is greater than 0 if the angle is less than 90. So the dot product will be positive. It's equal to 0 if theta is equal to 90. So dot product of two vectors will be 0 if theta is 90 degree or they are perpendicular, and it is going to be less than 0 if theta is greater than 90. So dot product of two vectors will be negative if theta is more than 90. Okay, next application of dot product is checking orthogonality or checking orthogonality. Or to check orthogonality is simply the property of one vector being perpendicular to another vector. So to check two vectors are orthogonal, what we do is we do A dot B, and A dot B is 0 That means theta is 90 degree. Let's take an example. Say I have a vector 2 cap plus 3j minus 4k, and b vector is, let's say it I cap minus 2j cap, then what is going to be the k cap? Minus k cap. Then if you compute a dot b, it's going to be 0. And from this we can infer this vector a and this vector b, they are perpendicular to each other. Now the next application of this dot product is going to be computing components. So we want to find components of a vector along n cap, which is an unit vector. So what we want to find is the component of a vector along a particular direction, which is n cap. Let's take this as our unit vector n cap, and let's take this as our a vector. So this is the direction of our n cap. Sorry. This is the direction of our n cap. So the component of a along n cap is nothing but this distance. And if this angle is theta, and this is right angle triangle, this thing is nothing but a cos theta, right? So magnitude of a, let's write it as magnitude of a cos theta. Magnitude of a cos theta, this is my component of a vector along n cap. Now this can also be written as a vector, magnitude of a vector, magnitude of n cap, because this is anyway 1 multiplied by cos theta, which is nothing but the dot product between a vector and n cap. So a vector dot n cap. So if we want to find component of a vector along a particular direction, what we would do is we would dot the unit vector along the direction with that particular vector. So from this we can say that component of a along x is a vector dot I cap. We can write component of a vector along y is a vector dot j cap, and along z it will be a vector dot k cap. Now we could have introduced components along a particular direction, like I could have introduced component of a along I directly, but instead of doing that I have introduced component of a vector along any arbitrary vector n cap. Well, I have introduced it in this way because in physics we find problems, or we find situations where breaking components of a vector along two perpendicular direction, where the two perpendicular directions are not of x and y, becomes important. So there are situations where we resolve the two perpendicular direction which is not the direction x axis and y axis. And one particular example of that, well, let's take that example. Let's say we have a pendulum which is swinging. So the pendulum is swinging along this circle. So this is my y-axis and this is my x-axis. This is my string. The weight of the pendulum is acting downwards. This is the weight, and the tension of the pendulum is acting along the string. This is tension. Well, in this case, we define two more. Instead of taking component along x-axis and y-axis, we define two more directions. We break components along this axis. This is the tangent of the trajectory. This is the tangent of the trajectory, and along this direction, this is n cap, this is the normal of the trajectory. So in this case, we compute the component of f along the tangent of the trajectory and component of f along the normal of the trajectory. Then we solve this problem. Well, I will not discuss how to solve pendulum problem here, because that will be in the course of mechanics. This is more or less about dot products. I would suggest students to compute and do numerical calculations on products as much as take any book and solve all the problems, and once you have gone through enough exercises of vectors, you will be very confident. Dot product is not a very hard thing. Dot product is a easy topic. End here, and thank you for watching.